Hey guys, welcome to CodeChef's YouTube channel. The problem that we are going to discuss today is yet another MEX problem. The problem appeared in long challenge of October 21 and has a difficulty level of easy medium. The prerequisites to solve this problem include binary search. The problem statement goes as follows. The max of an array is the smallest non-negative integer that does not belong to the array. So this is the definition of max. You can see there are some examples given over here to explain what does max mean. So in the first example you can see that the max is clearly 0 because 0 is the smallest non-negative integer that does not belong to this given array. Similarly, there are two more examples which you can see. Now the question goes as follows. We are given an array A of length n and we have to create a list B containing the max of all subarrays of A. So there are many possible subarrays, right? You can choose any two indices and the subarray starting from the leftmost to the rightmost. We can find the max for this subarray and put it in the list B. So like this, we have to calculate the max for all the subarrays and append these values in the list B. Okay. Now, after we create this list B, the problem says that we have to find the kth smallest value in the list B. So let's understand the same using an example. So let's say we have three numbers in our array and the k is given as 4. So the array A is 1, 0, 2. So the subarrays starting at the very first index will be, there will be one subarray which will be just 1, and there will be another subarray 1, 0, and then 1, 0, 2. So you can see what are the max for all these three subarrays. For the first one it's 0, for the second one it's 2, for the third one 0, 1, 2 all are present. So the smallest non-negative integer not present is 3. So we have got three values which we have to append in the list B. So let's keep creating the list B as well over here. The list is like 0, 2 and 3, and we have to add more elements as well. These were just the subarrays that began at the very first index, that is index 0. So now let's calculate the other ones. The subarrays starting at this index, they will be just the single element 0 and the subarray 0, 2, right? So this subarray, the max will be 1. The second subarray, the max will again be 1 because 1 is the smallest non-negative integer which is not present. So again we have to append both of these over here. So 1, 1, that is done. And now we have to see the subarrays that begin at the last index. So first index is done, second index is done, now the last index. For the last index there is only one subarray possible, that is single element 2. For this the max is clearly just the element 0. So we append that in our list B. So you can see the total how many values have we got? 1, 2, 3, 4, 5, 6. And that is clear as well because 6 is the total number of subarrays we can get with 3 elements, right? So once we have this array B, of course we need to sort it to get better visualization. So after sorting, B would look something like this. There are two zeros, there are two ones, and then there is 1 2 and 1 3, right? So once we have it sorted, we have to find the kth smallest value in the list. So k is given as 4. So you can see that the fourth value in this list is 1 2 3 4. So this is our answer. Okay, so 1 is our answer. So for this example where n is 3, k is 4 and a is given as 1, 0, 2, the answer comes out to be 1. How? We just, for the sake of explanation, what we did just now is that we found the max for all the subarrays, put them in a list B, sorted them and then found the kth smallest value. But this is not going to be the case in the actual solution. Why? Because as n grows, the number of subarrays will also grow. Okay, so it is not possible to find the value manually for each of those subarrays. So, but the question should be clear what we are trying to find out over here. This is the overall thing. Now the only task is that we have to do this in a more optimized manner. Let's see how. The solution approach goes as follows. First of all, we need to know that what our answer is going to look like. What I mean by that is that we are given an array A of integers, and from that array of integers we find another list B which contain the maxes of all possible subarrays. Also, it is given that the length of the array A is n, and the integers in the array A can lie in the set 0 to n. Okay, so the integers present in the array A will only be of this range, that is 0 to n. These are total n plus 1 integers if you observe, and this positions that we have available are only n, right? So this confirms that the max of the any subarray or the whole array A will also be in the range 0 to n. Why? Because there are only n positions, so you can fill them with only n distinct numbers from these. So one number will remain, okay, in the worst condition. So that also means that the list that we have B, the elements in this list will also be either 0 or 1 or 2 all the way up to n. Okay, so the numbers in the list B will also be from the range 0 to n. And since we have to find the kth smallest element from the list B, it means that our answer also belongs to this same range, that is 0 to n. So now we have reduced the search space for our answer. That is, we at least know that our answer is some number that lies in the range 0 to n. How did we come to this conclusion? Simple. We took the idea from the length of the array A and the integers present in the array A. From that, using the logic of MEX, what does MEX mean? It is pretty obvious that the integers in the array B, the list B, will also be in the same range, that is 0 to n. Hence, our answer is also going to be in the same range. So this is the step one of the thinking that I did while solving the problem, and I'm sure many of you might have figured this, but how to use this reduced search space to our benefit, let's see that. So now that we have established that the answer is only going to be one of these numbers, that is from 0 to n, the question now stands is that exactly which number is our answer. So to exactly find the number that is going to be our answer, we are going to use the method called as binary search on answer. So some of you might already know the well-known binary search, but binary search on answer is something different. So if you are new to this topic called as binary search on answer, I strongly suggest that you read this article on USACO about binary search. It has beautifully explained like when can we apply binary search on answer and all the usual questions and question types where this method can be applied. So you can read in detailed article over here. I am going to explain in short how it is helpful in our question. So coming back to our question, so these are the possible answers, that is from 0 to n. So this is our small search space in which our answer is definitely present, but we don't know which number. So one very common case where binary search on answer is applied is that if you have a search space which is first of all sorted, that is as we have our search space that is 0 to n, and in that search space if you have some monotonic function that is either an increasing or decreasing function, then you can apply binary search on answer. What I mean to say over here is that, for example, if we have f of x which yields true, okay, so true for some first set of numbers, and then suddenly it yields false, and then forever it will yield false, okay. So till some particular number the value of f of x was true, that can be interpreted as 1 as well, because true is 1 and false as 0 binary numbers, or binary values. In that sense, it is also monotonic, right? So if you have some function which on giving the our search space number as a parameter is yielding true up to some point and then suddenly yielding false for the rest of them or vice versa, in that case you can apply binary search on answer. Why? Because generally in such cases the question asked is that for the value of x having the f of x as true, we have to find maximum such x. That is, in this case, it would have been 4 because 4 is the maximum x such that the value yielded or the function yields true. Okay, such questions are mostly asked. So if we can find a function for us for our question which yields this kind of output, then we have solved our question. Why? Because we will convert it to a well-known problem like this. That is, find the maximum x where the function yields true. Okay. So now the question is that we need to find some function. So that again can be done after reading the question carefully. Why? Because we have been asked the kth smallest one. It means the answer, the array B, if I represent it over here, the array B will be something like this. Okay, it will be a lot bigger than n elements because total number of entries in array B will be n into n plus 1 divided by 2 because that is the total number of sub-arrays that you have. Okay, so from these many entries, we want the kth smallest. Let's say the kth smallest element is this one. Okay, so these are the first k elements. If these are the first k elements, then obviously, including this element, these are the last n into n plus 1 divided by 2 minus k plus 1 elements, right? This is the count of the elements from the right? uh, kth, kth element from the left is this element from the right. As simple as that. Now, once we have this number, what we know is that for whatever numbers that are present over here, for simplicity, let me just write some sample values like 0, 0, 1, 1, 2, 3, and so on. Okay. So for these numbers, the count of elements to it right. So let's say if I am considering this number as my current x, okay, this same x, these x are same, okay. If I am considering this as my current x, this count is definitely greater than this value. Let's call this val, okay. The total number of sub-arrays, that is basically the number of elements to the right in this array B, is definitely greater than this val, right? Same is the case for this, as for x is equals to 0, for x is equals to 1, for x is equals to 2. So basically what you can see is that for all the elements that are present to the left of our kth element, this is our kth element, okay. To the left of our kth element, the function that is f of x, that is count subarrays of x. What does count subarrays of x return? Count subarrays of x returns the subarrays that have their max greater than or equal to x. If this count subarrays of x value, if this is greater than or equal to this val. Okay, so this is a Boolean function now. So this Boolean function is exactly equal to this, what we just talked, right? It will return true for some first set of numbers and then suddenly it will start returning false, right? And the val is such that it is configured according to the kth element that we want to search for actually. So what we now have to do is we'll apply normal binary search, that is the initial range will be from 0 to n. We'll apply on the middlemost value. If the function returns true, it means that the current number is a possible answer and the answer may lie to the right as well. So we reduce the search space, that is we exclude the left half. Okay, if let's say we get true for 5, it means that the answer does not lie in 0 to 4. The answer either is 5 or some number to the right of 5. Okay, so this is basically the idea behind the solution. It will be more clear when you see the implementation. So the implementation is one of the most important part in this question. Why? Because writing the binary search code is only the smaller part, because it is the standard code, right? We just initialize the variables like l is equals to 0, r is equals to n, and then we run a while loop, and then each time we calculate the mid and so on. But what this function does, how this function works, is actually important. That is the count subarrays function. So that we are actually going to see in the code implementation itself. So let's start with the code implementation. So the implementation goes as follows. First, we take the input for number of test cases, and then for each test case, we take the input n and k, and also the input for the array. Now, after we take the input for the array, we have our variables set for the binary search, that is l is equals to 1, r is equals to n, and answer equals to 0. Okay, now we apply binary search on this range, that is from 1 to n, and in the binary search we always calculate the mid. We also have the value val, that is here named as mx because that is the maximum number, or actually the number of elements present in the array b. Okay, so that is that. And the condition for reducing the search space in the binary search is that we call the count subarrays function. Now what the count subarrays function does, the count subarrays function returns the number of subarrays having their max greater than or equal to mid. Okay, it returns the number of subarrays having their max greater than or equal to mid. Now, if that count is greater than equal to mx minus k plus 1, it means that it is one of those values who yield true, as seen right in the solution approach. We saw that the value yielded was true, 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 true for some first set of values, and then suddenly it was false. So this just means that the value mid is one of those that is yielding us true. So if it is yielding us true after comparing with this, so it means that it is one of the possible answer. So we set our answers as answer equal to mid, and then go to the right search space. That is, we simply do l is equals to mid plus 1. So if you are familiar with binary search on answer, this thing is a pretty common thing to you. The only thing that matters is that how you write this function. Okay, in binary search on answer, there is usually a boolean variable that decides whether to go left or whether to go right. Okay, so here that main job is done in this function. So let's now understand how this function works. That is, how do we count the subarrays for which the max values are greater than equal to mid. So the function looks something like this. Here the mid value is actually stored in the variable x. Okay, so we have a variable int x. So now we have our array A with us. The array will look something like this, right? The array will be something like this. It will have elements A1, A2, A3, and so on, right? A1, A2, A3, up to AN. Now, first what we do is that each time we call this count subarrays function, I initialize the count of each number. So this is different array. Okay, CNT is a different array. It is just responsible to keep a track of the frequency of elements. So you can call it like a frequency array. Okay, so each time I call this function, the values are reset. That is, the frequency of all elements is currently 0 because I haven't yet actually seen the elements. Okay, I just run a for loop from 0 to n and set their frequencies as zeros. Now I want to, what does the sorry, what is the main motive of this function? The main motive is to give me a count of MEX greater than equal to x. Okay, count the subarrays having MEX greater than equal to x. So for that, first I I apply a two pointer method. So this two pointer method is going to look something like this. The left pointer is kept on the very first element, that is the index 0. Okay, I is equals to 0, and then I keep on moving the right pointer towards the right by one position each until I find the subarray starting at index 0 and having their max value as x. So how is that done? Initially max value is 0 because I haven't seen any elements. Also the right pointer is also present where the left pointer is. Okay, and while r is less than n and max is less than x, I increment the frequency of the current element. So frequency of a1 is incremented, then frequency of a2 is incremented, and so on. And once the frequency is incremented, I also increment the r pointer. Okay, and after r is incremented, I check for this current subarray what is the max. How to check that? Simple. Because max is the smallest non-negative integer, max is initially set to 0, and I find the smallest value of max for which count of max is 0. That is basically my actual max, right? That is why the frequency is very helpful over here. So if you have solved questions that involve max before, this will be a common thing for you, writing a loop like this. While count of max, max plus plus. This basically tells us what is the current max. So now that I have found the subarray starting at index 0, which has max equal to x. Okay, after that is done, I have to check this condition. That is, if after doing all this, if the max is still less than x, it means that this condition is not at all possible, right? Because I have checked all possible lengths subarrays starting at index 0. So in that case, I just return 0, base condition. Okay. If not, I have to set my answer. That answer is basically the count of subarrays. So answer is basically the variable that we are going to return in the end. Okay, this function is returning. So I have to set answer to n minus r plus 1. Now why n minus r plus 1? Say the right pointer is finally present over somewhere here. Okay, so L, the left pointer is present over here, right? The left pointer is present over here, the right pointer is present over here. So these elements, these count of these elements is what is basically n minus r plus 1. Why? Because if the subarray from L to R has a max x, then all these subarrays will also have their max greater than equal to x. This is implied. So how to count those subarrays? We keep L fixed over here, and R can go from anywhere from here to the last position. That is why we have our answer variable as n minus r plus 1. Now, once this initial subarray is done, we now start incrementing the left pointer one by one. So left pointer will increment by one step each time. Okay, so left pointer is going to increment by one step each time. Now, when the left pointer goes to somewhere here, then the earlier elements count should be removed, right? So we remove that first. Okay, if you can see over here, I'll highlight it. Uh, yeah, over here you can see that we remove the count of the previous element. That is not in consideration. And now because that element is removed, we have to check whether that frequency became 0, because if the frequency became 0, then our max has changed. So if our max has changed, we again increment the right pointer until we find the same element. Okay, until we find the same element, we increment the right pointer. So like this the two pointer approach goes. First we kept L fixed at 0 and we incremented the R. Then once we got our initial first subarray, after that we just keep on incrementing L by 1 and similarly adjust the right pointer. Now there is this one more condition, that is, if you reached all the way to the end and still couldn't find the element that you removed, like for example if the element over here was 0, if the element over here was 1 and so on. So when you brought your left pointer over here, this 0 was removed, right? So your answer might have changed, that is your MEX might have changed. So you need to find a 0 in these remaining elements. So if you couldn't find it till the very end, it means that there's no point in looking the further subarrays. So you break over there. Or else, again, wherever the right pointer was present in the end of this for loop, from there till the end, the count will be added to your answer, n minus r plus 1. So basically, we are counting how many subarrays are there having their max greater than equal to x. This two pointer method is also pretty well known. You might have to look at it twice or thrice to get a better understanding of it. But yes, once you understand this method, you will applying binary search on answer will be very easy for you. So we finally return the answer as the count to our function call over here, and then we check whether it is greater than or equal to mx minus k plus 1. If yes, we have found possible answer. Okay, this is one of the probable answers, and we increment the L to mid plus 1. So basically go to the right hand side in our search space, and as binary search works, it will in the end land towards the actual answer. So once this while loop is over, we finally output the answer, and that completes our solution. So I hope you guys understood the solution approach and the implementation. I understand that the implementation will be hard to understand for those who are new to this concept of binary search on answer, but please first read the article that I suggested, the USACO guide. Okay, the USACO guide is very helpful and very it states the main cases where you can apply binary search on answer. Okay, the well-known problem types, and once you understand this, then understanding the code will be very easy, because you don't need to understand this part. This will be a very common part. The only thing that you need to understand is the function, count subarrays function. So that brings us to the end of the solution.